Hey guys, it's IDW, and today we're going to be taking a step back to this original serial, also known as Ripple Carry Adder, because there's other ways just than building a parallel adder to actually fix this problem. You still can make something that's technically serial, but is actually faster than this thing. And the way that we're going to do that is we're going to take a little page from this Incrementers right here's a book. Because if you remember, we were using these guys right here as AND gates. So yes, pistons can actually be used if you cut off a signal, just like I showed when I was originally making this thing, as AND gates. So basically what we're going to be doing is, instead of just taking it in through this and ANDing it with this, we're just going to use a piston to make it so that the AND gate goes through it. Well, the AND gate isn't, like, sluggishly slow, anyways. So, yeah, this is a common, popular type of adder that is called a instant carry adder, and, yeah, it's faster than this. This guy actually does have a few advantages, not including it's not as messy busing, but, yeah. So see you guys in a second, and we'll actually start building this thing. Because that's really all you need to know. We're using a piston AND gate instead of an AND gate with two torches. So yeah, we can just really easily build one of these things. And the instant carry adder that I'm going to be building right here is going to be one that I designed myself, and I've shown it off in a previous video. It's a pretty nice design. And yeah, there's a whole bunch of designs out there, but all you really need to know is you need to see how the carry logic works for this thing, and then you just need to compare it to... basically, you just have to see how it works, because it's a bit more difficult if you didn't get the explanation of using a piston AND gate instead of a normal one, but yeah. So all I'm going to have to do is I'm just going to have to bring this guy down like this guy like that, and yeah. This design is actually the first, oh, that's the first time I've ever done this in this world, yay. Normally I do that a whole bunch. Anyways, this is the first time that I'm actually going to be using slabs in this series. Actually, I used them over here a bit, but I didn't really go over what they are and how they're useful. But, yeah. I'm assuming that you know what they do. It's sort of like glowstone, if you've ever heard of people using them like that, but I think from looking right here you can see what's going on. Basically, a redstone signal cannot flow down a slab, but it can flow up it. So, yeah. Oh yes, also, right here, this is actually a new XNOR design that I've never used before in this series, and it really goes off of the fact that... Oh, and by the way, one thing I forgot to mention, since the piston does technically have to be in an inverse state, we're going to have to use an XNOR instead of an XNOR to make this kind of adder. But anyways, there's a... okay, so basically, the way that this XNOR works is it's a NOR gate or an AND gate. So a NOR gate, if you've never heard of what it is, it's basically a logic gate that its output is on if no inputs are on. An AND gate, you also might know, is a logic gate whose output is on if only both of the inputs are on. So if you think about it for a second, that fits in with the truth table of the XNOR gate, because the only time that it's on is if both the inputs are on or both the inputs are off. So yeah, that's basically how that works. Anyways, so now we can just build this guy, and I'm going to use the AND gate from down here as part of the carry line. So yeah. because we're still generating it in the same way. And by the way, this right here is the actual piston that we're going to be using to and the stuff. So basically, first of all, we have to have a carry coming from right here. Well, some bit that's been in the past. And second of all, this has to be off, which is sort of like we're ANDing it with the sum, right? And that's the only case in which it can be on. If you understand pistons, then you should understand why that works. But yeah. So I'm not actually going to be building the ALU part into this, I'm just going to be building the actual thing. So no flood carry and cut carry. Some people who are watching this series might not actually understand that, so yeah. Anyways, just the second, oh, by the way, this is another XNOR design that works really well. If you think about it, also, an XNOR is sort of like you're choosing to either use an identity gate or an inverter with your, what's it called, inputs. So for instance, if I was to take a normal, what's it called, XNOR gate, like I have right here, or XOR gate, and I'm just going to invert the output so that it becomes an XNOR gate. If I was to turn one of these guys on, then the output right here, right now, should be just the same as this gate right here. And I just showed you both states, so yeah, it is. But if I was to turn this guy off, then it would be the inverse of this guy. So that's basically the idea behind this design of an XNOR gate. We are using a multiplexer to choose between, oh, by the way, that's just something that allows you to choose between two different wires using a piston, like I have right here. Well, it doesn't have to use a piston technically, but it's choosing between either the carry data or the inverse of the carry data to XNOR with the first sum. So that in turn will give us another XNOR. So yeah, that's basically this whole instant carry adder finished up. Sorry if this was a bit confusing, but it really is just one of these guys, only this AND gate right here is a piston. That's really all it is, and all you need to understand from this video. So if you didn't get, if my commentary wasn't the least confusing that it could be, then if you just understand that, and that that's possible, you'll be just fine. Oh my gosh, I hate it when I do that with World Edit. See, I chose both the second position and the... I chose the second position as two different spots. Anyways. So, yeah. Here is our carry line. Well, our adder. So just to test that this is in fact working, 11 plus 3. Sorry, 11 plus 1. Wait a minute, so then... Oh, yeah. And as you can see, our result is 12. And just for people who want to see 5 plus 3, I will, fine. That's very fine. 5 plus 3 should be 8. Ta-da! So yeah, this is a working adder, and as I said, it is actually faster than this one. Well, this one down here. So yeah, nice adder design. And there is one last thing that I want to note about this design, and that is it introduces something called a rising edge, which is basically something a little more advanced, but it basically means that it's only this fast when the inputs immediately turn on. If you use a synchronized XOR gate for your first XOR, like the Tommy's XOR right here, then you won't actually have that. But with this design, it is actually rising edge. It is a bit faster on the rising edge. So yeah. So that basically, okay. So that means that when the input first comes in, your inputs have to come in at the exact same time. Otherwise, it might be a bit slower than it can be at fastest. But yeah. I hope that you learned at least a bit from this, and I'll see you guys next time, where we're going to be skipping Ladner-Fisher adders, which a lot of people do, well, a lot of Redstoners do, and we're actually going to be moving all the way up to Carry Look Everywhere. Not because I don't like Ladner-Fisher adders, but it's just that I really... Well, I just said that it's not that I don't like them, but I really... The logic that goes into them is really confusing, and this is supposed to be a more basic one, and if you understand Carry Look Ahead edition, which is just parallel edition, then you should be able to understand Carry Look Everywhere edition. And Carry Look Everywhere edition, believe it or not, is the end of this series. So, yeah, we're almost all the way through. Pretty much most of what there is to know about adders. So yeah, see you guys when we're going to be building Carry Look Everywhere adder.